Hey folks, for this discussion we're going to talk about the torque on a loop of wire that's carrying a current in a magnetic field. And please take a moment to pause the video and basically copy this diagram down. What we've got here is a magnetic field pointing to the right, and we've got a rectangular loop of wire that's carrying a clockwise current. So if you need a moment, go ahead and pause the video and copy that down. All right, so in the previous video or discussion, we did talk about if you have a loop of wire in a magnetic field, the total net force on that loop is 0. However, that doesn't mean that it doesn't move, okay? So the net force on this loop will also be 0. But what happens, okay? So what you have here is you have 4 separate wires, so I'm going to look at one at a time. So let's look at wire 1. Okay, if you do your right-hand rule, this is a top view, by the way, like imagine you're looking down on your desk, and there's this rectangular loop of wire carrying a current, and there's a magnetic field pointing to the right created by probably a bar magnet or something. So if you look down on this and you look at wire number 1 there on the left, the current is going up the page. So if you use your right-hand Lorenz force rule, you point your hand up the page, and you have to rotate your hand until your fingers curl with the magnetic field to the right. And when you stick your thumb out, your thumb's going to point down. So there will be a downward force, so I'll use a different color. There will be a downward force on that left-hand wire number 1 there. So I'll use an X to denote into the page. We'll do the same thing for the other 3 wires. Now wire 2, it's running parallel to the magnetic field, so it's not going to experience a force. Wire 3 is got a current running down. If you put your hand facing down the page and then you rotate it so your fingers curl to the right with the field, your thumb will point up out of the page. So that would be that force. We'll call that F3. Oh, and the other one we'll call F1. Okay. And then finally, wire 4 doesn't have any force on it because it is also parallel to the field. So what's this wire going to do? Well, the left-hand side will go down and the right-hand side will go up. It's going to twist or torque. Okay. So the amount of torque you're going to experience, it's going to depend on the current and the other dimensions there. Before we go ahead and calculate that, I want to draw a couple other views of this. So imagine that this is the top view of this. Imagine that you stood here and looked, parallel to the desktop. Okay, so then your magnetic field would still be pointing right. Okay. But now you would be seeing this, you'd be seeing this wire in the front. And so what you would see is just the edge of this whole thing, okay? And this would be the wire current going into the page. So that'd be, I'll draw a little X there for that current. And then there'd be a current coming out of the page here. So that would be a current there and a current here, okay? And then these forces would be down, so that's our F1, and up, that's our F3. So there you can kind of see the torquing a little better in this view. This would be it'd be a front view. Okay. Now, if this thing torques a little bit, it's going to start to rotate, in this case, counterclockwise. So I'm going to draw this front view again a moment later. Okay, so here's our magnetic field being made by a bar magnet or something. Okay. Now here is our wire. Now it's rotated some. We still have these 2 currents on each side of it coming in and out of the page. And this force, this F1, will still be straight down, and this F2 will still be straight up. Okay. Okay, so we'll come back to that picture in a second, and we'll talk about the angles there. But for now, I want to focus on these 2. So how much torque does this loop experience? Well, hopefully you kind of note that it's going to rotate about its center here, okay? And I've given this thing dimensions A and B. So this dimension would be A over 2 from the center to one edge. So the force, we'll start with the force. So F1 would be I L cross B, okay, which would be I times the length of wire B, which is just B, little b, and then times the magnetic field. And that's into the page. F2 equals F4 equals 0. And F3 is going to have the same exact magnitude as that. It's just going to point the other way. Okay. So what's your torque? Okay. Well, the torque created by wire 1 is torque is defined as R cross F. Okay. What's the radius here? Well, this radius is A over 2. So you get A over 2 times the force, okay, which is I times little b times big B. Okay. Torque 3 will be identical. Okay. And then the torque created by wire 2 and 4 is 0 because the force is 0 on both of those. So your net torque on this thing would be double this. So it'd be A times I times little b times big B. And another way to write that is the net torque equals I times AB times the magnetic field. Well, what's AB? Well, that's just the area of this rectangle, A times B, right? So you get the following. You get I area of the loop times B. So that way, if it's not a rectangle, if it's something, a different kind of shape, you could still easily, if you know the area of it, you can calculate the torque. Now, we kind of write it like this, okay? And area, in this case, actually is a vector. So let me explain what that means, okay? What you do is in this top view, if you if you curl your hands with the current. So if you imagine curling your hands clockwise, your thumb points into the page, okay? That's the area vector. In this view here, the area vector would point, if you kind of curl your fingers with the current, the area vector would point that way, okay? And in this view, the area vector would point that way, okay? And the area vector is perpendicular to the area of the actual loop, and the magnitude of the area vector is equal to the magnitude of the area, okay? So this cross product, the angle we're talking about here, is that angle right there, the angle between the area vector and the magnetic field. Now, in this portion right there, that angle is 90 degrees, so you would do sine of 90, which is 1. Here, the angle is less, so you would get a smaller torque. Eventually, when this thing became vertical, the net torque would be 0, and if there's a little friction or something, the thing would just kind of stop there, okay? Now, another math thing I'll discuss briefly. This product of IA, we give it a symbol. Now, if you're doing problems in the book, I don't really care if you use this, but I times A is defined as a mu, and that is called the magnetic dipole moment. There's no need to calculate that, but if you decided to, you could do that. And then your torque equation shortens to the following. It's that mu cross B, okay? Now, this is the beginning of an electric motor. So let me kind of show you. So what you have is you have your loop of wire. In this picture, the magnetic field, which I will use the same color I used in the other notes. So magnetic field goes from the north to the south pole, so the magnetic field goes like that, okay? So if I look at the forces acting on that wire, okay, the wire with the left-hand wire here, the current's moving kind of out of the page at us. I rotate my hand until my fingers curl to field kind of to the right. My thumb points up. So this wire will be forced up, and likewise, this wire here will be forced down. So that would be your torque. And so this thing would start spinning clockwise. Now, it would spin clockwise until, this is like a battery here, it would spin clockwise until you hit this little break in this little device here. It's called a commutator. And the idea is, once this wire got to the top, this thing would stop. But this little commutator then reverses the current. And so you get another half turn, another half spin. And then that repeats itself. What that looks like in motion is like this. So here's our loop of wire, here's our permanent magnet, these bright turquoise things, that's the commutator, here's your battery. When you play this, and I'll slow it down a little bit, so you can kind of see like the torque every half turn it keeps going. Now this one happens to be counterclockwise, but the idea is the current makes a torque, and then this little turquoise commutator reverses the current every half turn, so the torque is always the same way. Okay. All right. Oh, here's another kind of view of that. I think this view might be a little better. Okay. Well, let me go a little bit. Okay. So here you can kind of see the torque. The current in this wire right there is going away from us into the page. So if you point your fingers into the page, curl them to the right with the field, your thumb points down. That's these green force arrows right there. Likewise, this current comes out of the page at us. If you point your fingers toward your face, curl your fingers to the right, your thumb points up. That's these force vectors right there. So this is basically the beginning of an electric motor. You get a loop of wire with a torque acting on it when you put that loop of wire in a magnetic field. For us, what we need to know is that the torque is equal to IA cross B, and that's the easy part of that. All right, I hope that video was helpful, and thank you very much.